I'm using the slides out of the other book that's there, but again, I tend to use these slides more as a guide than right there. And okay, this is actually chapter 3 that there. I'm not really following the chapter so much. This is out of the book that I uploaded the other day on the e-learning. So you should have 2 books for this class right there. One is the one that I gave you on the thumb drive the first day of class or second day of class, and that's the primary one that's deployed. The other one is the one by Tochi, Whitmer, and Moss. I actually know the authors of this book because 2 of them I worked with at Purdue. I'm surprised that they put their name on the book because they actually did write the book. The book was written by Tochi many years ago, and they just updated it, list themselves as co-authors. But that's kind of a discussion point with us, with the folks at Purdue. We argue about that there. So I'm more familiar with this book since it's got ties back there. So we're going to be looking at the basic gates that there, and we're going to look at them in more detail right there. So I should turn these off. We're going to look at the Boolean expression. We'll talk later about De Morgan's theorem. De Morgan's theorem is actually probably the lecture that I'll be recording is on De Morgan's theorem out there. And we'll end up talking about universal gates up there. And active low, active high, propagation delays, we'll talk a little bit about that. And then we'll get into a little bit of HDL at the end of this chapter that there, if I follow this chapter now. We won't follow this all today by any means. We'll probably just get through the 5 basic gates. And I'll go through a little introduction to the software that we'll be using for doing our lab assignments out there. So, all right. Boolean algebra, we said this before, this is all review, slides, that's the problem with using other people's slides, that there is, logic 0, logic 1, that there, and basically we said in previous lectures that usually a high is somewhere between about 3.3 volts on up to 5, and everything down below 0.7 volts to ground is considered a low. Those numbers vary greatly between logic devices. I'm not going to require that you remember the voltage levels out there. But again, we've got logic 0, logic 1, false, true, you'll use off, on, low, high, logic, no, yes. These are all different terminology that we'll use. Now later on we'll talk about something called active high and active low, which totally confuses things because it reverses some of these discussions. But for right now we're looking at active high, which means that if a voltage is high, that means that it's active. Right there. So, right there. So there's 3 basic logic gates there, and or not. We'll look at those, and then we got various variations between them. Now we're going to spend a lot of time talking about truth tables, and I went through some of these truth tables the other day, but we'll just kind of look at it there. A truth table is basically a table, and you can do it in Excel, you can do it on a piece of paper, you can do it in Word with a table. There, most of you would probably do any homework would be done in Word, so you would just insert a table for that there. So if you have 2 inputs, you would have 4 entries. You would cover all that there. If you have 3 inputs, it would be 8 entries. If you have 4, then you would have 16 inputs. So this is basically an example of some truth tables right there. And again, what we've got here is we've got some function of A and B. We don't know what this function is right there. And we have an output called X. Now later on, I'll talk a little bit about the fact that sometimes we shouldn't use X as our output, because if we use the software, particularly the Altera software, X means something else. Actually what it means is don't care. X is quite often, is one of those things that it's used for variables in algebra forever and forever. But when people did Boolean algebra, and they set up later on when we look at at a Karnaugh map. We'll be looking at Karnaugh maps, and whenever you have an X, that means don't care. You essentially ignore that input. It's a don't care. But for right now, we'll use X as our output right there. So A and B, this is a function. And what we list here is A and B are our two inputs, and we list our 4 possible states. 0, 0, 0, 1, 1, 0, 1, 1. And if you put this in binary, that's 0, 1, 2, 3. If you did that decimal. This output right here, there. So this output happens to be true if A and B are both false, or if A is true and B is false. So I can actually write this function. And where's my pen? Here's my pen. I can tell you what this function is. We'll look at this right there. This function here is going to be X is equal to A naught B naught or A B naught right there. And later on I'll show you how I come up with that. But that's what's inside this function right there. And that's going to be a series of gates that there. We'll look at that there. But this is how we define a digital combinational circuit. This is the same thing, only we've got 3 inputs. A, B, and C, and X right there. And this last one we stick D on there. It's not a very good looking D, but right there. So we've got D. So again, this here is our output right there. And sometimes if you're given a design problem, you're given, this is what we want our function to do. Here's our truth table. You have to come up with a logic to do that. And we're going to learn how to do that. That's one of the early goals of this class. The other thing you might be given is you may be given a circuit and be asked to generate the truth table for it. So what we have here is basically we have a series of inputs, and we're going to stick to basically 2, 3, and 4 for right now, inputs. We have some type of logic in here. This is a circuit that's inside this little black box. We don't know what's in there. And we have an output for it. Now we can have circuits with multiple outputs right there. But right now we're going to stick with just one output right there. So a Boolean expression right here is here. This says that this is X is equal to A or B. The plus sign is the OR in the digital world, right there. And the OR looks like there. 1 plus 1 is equal to 1, not 1 plus 1 is equal to 2. And that goes back to the truth table right here. This is the truth table for an OR gate. This is the circuit for the logic symbol for an OR gate. So as we look at our truth table, if either B or A are true, here that's true. This one's true. So these are true. Here they're both true, so this is definitely true. So this case, neither of these are true, so this is not true. Right there. So that's there. So you have a situation where it's A or B right there. And this is the circuit we would show for that right there. This is right there. And it's the standard circuit. You're going to be drawing that there. We've got about 5 of these you have to just basically memorize. Right there. The OR gate is the first one. Right there. This is the 3-input OR gate. Right there. Same basic logic there. An OR gate is actually fairly simple because the only time it's false is when all the inputs are low. That's the only time that a OR gate, and you can have a 4-input OR gate. You can have a 6-input OR gate, 8-input OR gate. Right there. So you can have multiple OR gates. Here's a case here where we've got an example. It's not a very elaborate example, but what we've got is we've got some type of process right here. We have a temperature sensor right here, right there, and we're comparing this to some known temperature. So if it gets too hot, this output's going to go high right there. So this is a comparator. It's actually just a 741 op amp. We have some circuit looks like this, a pot where we set threshold. This is our input. This is our output. And if this input goes higher than the threshold or our set value, the output goes from 0 to high. Right there. It's a simple little comparator circuit right there. I don't know if have you had op amp circuits out there? Out there? An op amp is just an amplifier. It's got a very high gain, and if you use it without feedback, that there, basically it will operate as a comparator. So it looks at two inputs. If VTR is higher than VT, the output is low. If VT is higher than the threshold, the output is high. So it just compares two voltages, is all it does, right there. It's an analog circuit, right there. So we have our temperature. So the output of our comparator says that the temperature is high. Here we also have a pressure transducer. A pressure transducer is a basic component that has as its input some type of pressure sensor. They make them, for example, in automobiles to measure the pressure in your tire. That uses a pressure transducer right there. They actually build them. I haven't seen them in, I've got a Perdua, which is not the top of the line luxury car. I have to admit that there. It's a good car. Don't get me wrong. I'm not picking on it, but it's not a luxury sedan. Back in the U.S., I had a Buick LeSabre, which is the upper end luxury type car, and all the valve stems in the car had temperature transducers in them. So if your tires were were low, it would send a signal to the computer in the car telling me that I need to put air in my tire. So they built pressure transducers in the tires themselves. Actually, it wasn't in the tire, it was in the valve stem. When I talk about the valve stem, it's that little thing you put your air in on the tire. Inside that, it would actually measure the temperature and send through a radio signal to the car that it was under or over pressure. In about every 3-4 years, you had to replace it because the batteries would go dead in it. So that was built into it. So but what a pressure transducer does is it measures pressure and converts it to a voltage. Any type of transducer measures some kind of physical quantity, such as temperature, and changes it to a voltage. Temperature transducers, they make a series of little chips. I can't remember the LM317. No, that's a voltage regulator. I can't remember the part number. But there's a whole series of temperature transducers that the output is a function of the temperature. If you look at, if you put it on a breadboard and you take your fingers and you squeeze it and raise the temperature, you can watch the voltage go up. You put a piece of ice next to it, you can watch the voltage go down. It converts temperature to voltage. Same thing with the pressure transducer. It converts pressure to a voltage right there. And again, if you've got a digital tire pressure gauge, it's got a pressure transducer in there, and then the output of that is read, converted to a display that you can read the pressure in your tire. So again, this is the same thing. We've got a preset value that if the pressure goes beyond that, we know something's wrong with our chemical process. So if either of these transducers or comparators go high, we want to sound an alarm right there. That's all we're using this OR gate. Now this alarm doesn't tell me which one, whether it's a temperature or whether it's a pressure problem. It just tells me that my process is no longer under control. So we're using a basic OR gate. Another example of an OR gate is a very simple one. Right there. That page. Right there. I've got a house with 4 windows, 2 doors, and I have a little sensor on each of these right there that if I open the window or open the door, it opens that. These are all switches right there. So what we've got here is a 5 input OR gate that if any of these switches open at their, excuse me, close, then we sound the house alarm. Again, we don't care which window is open. All we know is that somebody's opened a window right there. Or I turn the alarm at night, and as soon as I turn the alarm on or activate the alarm, it goes off. That tells me that I've left a window open somewhere in the house. Right there. Which, if you live in a city like Kuala Lumpur, is not a smart thing to do. Maybe if you live, in a small compound, you can get away with going to bed with your windows open and your doors open. But I'd say in KL, that's probably not very smart, right? Not there. So. Okay, as we go through there, that's a basic that there. Same discussion with the AND function. Same type of discussion with the AND function. Again, it's basically x is equal to A and B, as shown as multiplication. Sometimes it's shown this way, or sometimes it's shown this way, right there. Just like if you're going to multiply 2 variables, y is equal to 3ab or 3 dot a dot b, right? That's basic algebra, right? Same thing. The output is true only if all the inputs are true. So this one's, as we look at these tables, it's very easy to look at the AND and the OR tables, because the OR table, only the top one is going to be a 0. Everything else is going to be a 1. The AND operation, everything but the bottom one is going to be a 0. Right there. So memorizing these truth tables for the AND or the OR is very simple. Very simple right there. So this is, again, same thing as what I was saying. The only place that's true is the last one. Right there. That's the only one that's true. Now, as you can see, we've got these 2 symbols right there. Right there. This is the OR. This is the OR. And this is not going to let me. Well, this is not going to let me draw. This has got all kinds of funky things going on up there. Got there. Okay, well, we won't worry about that there. This slide here actually shows what I was wanting to show there. The AND basically tells us that is high only when all inputs are high. The OR means that we'll go high only when any input is high. Or you can use reverse logic. The OR is only low when all inputs are low. Right there. Those are the 2 basic symbols. And you'll hear the term AND OR logic right there. The next one is the NOT. It's shown with a little bar over the top of it. There. Sometimes, and you'll see me do this on quizzes and on the final exam, is that you will see me use the apostrophe notation. The reason is this is hard to do on, up there. So as we look at this one right here, you'll see this one used more on anything than I'm typing there. If I'm writing an exam with Word, how am I going to put the little line above it? There's a formula editor that I can use, but up there. But putting the little line on it when you're using a word processor is not easy. So typically, people will use, if you're doing textbooks and you've got an equation editor, and you've got a proof, typesetter, then they'll use the bar. That there. But quite often, if you read papers, or if you read exams or quiz questions or something like that, you're normally going to see it written in this format right there. Right there. So now later on we're going to be looking at something, but I'll just go ahead and put it right. Let me do it this way. This is, if I have, okay, what is this doing here? Right. And my pen is not wanting to cooperate. Why is my pen not cooperating? All right, my pen is not cooperating. What is going on here? It may be a time to replace a battery. I've had this about 6 months, and I've got a funny feeling that my battery may be bad. If that's the case, all my technology is failing me. Okay, now, it definitely is a battery problem. One thing that you need to keep in mind that A naught, B naught is not the same as A, B naught. Later on we'll get into that there. But you have to look at, you see, and this would be written as A apostrophe B apostrophe, and this is not the same as A, B, parentheses apostrophe, right there. So later on, and we'll get into this in a little bit more detail, but you have to be a little bit careful on parentheses, and if you draw it this way, where the bar lies. Because if you look at the circuits there, what the first one is saying right here, this is saying that I've got an inverter, and this is going to an AND gate right here. So this is A naught, B naught. This is going through an AND gate, A, B, and then an inverter out here. So it's two totally different circuits. They don't mean the same thing. So, and we'll see more of that probably by next Tuesday. We'll get into that there. So as we look at there, and there. So it's normally often called an inverter. This little bubble right here is an important thing to look at, because this little bubble is going to show up from time to time. Back when engineering classes were mostly male, we used to call it something else, but we won't use that terminology here. We'll just call it the bubble. The little bubble is usually the inverter back there, because you can show that on an input too, right there. If I show this as on an input, that implies that in circuit-wise, I have an inverter going to here and no inverter there. So this little bubble right here, actually is the same thing as this right here. So the little bubble will show up on outputs too, right there. And we'll see that here in just a second. Here. An inverter just simply complements all signals on the waveform right there. So all it does is just inverts it right there. If the input's high, it's low. If it's low, it's high right there. So this is a typical, right there. If we push a button, that there, it just simply inverts it. We would probably never do this circuit right there. So this is basically the summarized rules. If you look at the three, now we're going to keep on going here. Obviously, we're not going to stop after 30 minutes today, but we'll keep on going. We can start drawing our expressions looking like this. This is a Boolean expression right here. X is equal to A, not A and B, ORed with C. Now, later on we'll get into the priority of things that there, but multiplication still takes priority over addition in digital. We haven't got into the rules of Boolean algebra. So if I have a function here, let's say I just write a function, and I want to say I want to take A plus A B naught plus B ANDed with C right there. How would I draw that? First off, I would take A and I would run it through an inverter right there. And I would go through an OR gate and take B there. And then I would have an AND gate and C right there. Right there. And actually, that's going from left to right. That's actually if I put the parentheses here. If I do it the other way, I got the AND gate. There's, if I take C and B, and then inverter right there. Actually, this is the right one. This one's wrong. This is if I put the parentheses in, because remember I do the multiplication first. And we haven't got into, so this is actually the right one right here. This is A not C. This is the right one right there. This one is if I put the parentheses. So I made the common mistake right there. Right there. These are two totally different circuits. And if I went through and did the truth table, I would get different answers for that there. In a few minutes, we're going to go through on how we would generate a truth table. And generating a truth table by hand is kind of a tedious process, but we'll come back to that there. Right there. So, unless there's a parentheses in the expression right there, you see, again, this gets back to what I was just talking about, where I put the parentheses on the addition first, right there. So, that's what I just showed in my example, is that I mistakenly did this first, right there. Right there. The AND operation will be performed first. Again, that's what I was saying. And then when I did the example, I made the mistake of doing it from left to right. But you do it adding first, do the AND first, right there. So that's just a common way of doing it. And we'll get into a lot of these Boolean expressions right there. Whenever an inverter is shown like that there, the output is equivalent. We put the inverter right there. It's present the output with a bar over it. So in other words, what I've done here is this is that A naught right here. And that's similar to what I just did a few minutes ago. This is A or B all knotted. And again, I mentioned that's not the same as A plus B, each with inverters. So that's different. That circuit would look like this right here, with an inverter on each one of these. Right there. That's this one here. Right there. So we get into right there. Further examples. Here we got something that looks much nastier. And this is a good final exam question. The only thing is on the final exam, if I were to ask this, I wouldn't give you this, 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 or this. Oh, I might give you X, Y, and Z to help you out. Here. So if I gave you this question here, I would say, what is X? Well, first off, I would look at X, and I would look at the inputs here. This A naught, B, that there. So X is equal to A naught, B, C, right? Y is equal to A or D. Then Z is equal to A plus D, all with a not because we got the not gate there, times A not B C, right there. That's it. Yep, that's right. So again, this is a nice little test question, you know, right there, something that would show up for the first part of the class. Right there. The first part of the class, there might be some twos, you know, some number, base 2 to base 10, base 10 to base 2, base 2 to base 16, some questions like that, and then we would get into some basic circuits right there. Right there. And this is a fairly straightforward type of question, right there, where you would see this right there. Again, we've got another one that would be the same type of problem out there. And I'll put these slides up so that you have these examples right there. So again, what we've got is we go back here. This is A or B. Then we end it with C. Now notice that we put the parentheses here. Those parentheses are important. Because if you leave the parentheses out, then it doesn't work that way. Then we invert that. So we go through each one of these steps. Then we take that, we OR it with D right there. And then finally, we AND that result with E. And we can come up with this right here. So this, again, is a very typical type of question you would be asked to do right there. Now, you could go the other way up there, where you're given a function and you're asked to draw the circuit for that, right there. So, the rules we're evaluating: we form all inversions in single terms, we form all parentheses with the parentheses, for AND. This is the one that everyone forgets, including myself a few minutes ago, right there. Has a bar over it, perform inside the expression, then invert the result. We'll talk a little bit about that there. Best way to logic made of multiple gates is use the truth table. Now, allows you to analyze one gate or logic combination at a time. Now, this one is very tedious. This is a tedious process we're getting into here, right there. Allows you to easily double check your work. But we go through here, and we've got this circuit right here. Right there. So as we look at this circuit right there, we're going to put 0, 0, 0 on here, and we're going to see this is going to be a 1, this is going to be a 0, so this is going to be a 0 right here. This is a 0, so this is a 0, so the output is 0. Then we repeat that with the next combination, and I'm hoping that these slides do that. I thought that they did. But we go through that for every combination right there. You know, so we would write this A, B, C, and so we would do 0, 0, 1 next. Well, that's going to be a 0 here. This is still going to be a 1. This is still going to be a 0. So it's still going to be a 0 out. And we do that all 8 steps at a time, right there. Again, another nice, neat little question that can be asked, right there. So, and we go through there, and what we're doing at this particular case, he's using intermediate values here in order to simplify the problem instead of doing it all at once. This is the actual final answer that we do that there. So we're saying that U is equal to A naught. So here's A, B, C. So here's U right there. And then we say B is A naught B. So then we go through and we fill that column in right there. So we fill that column in. So then we've got right here U, A naught B, and so right here 1, 1, and that's the only 2. And then the next column is BC, right there. And right here, we look at any place where B and C are both 1. Here's 1, and here's 1. Those are the only two. And then our last column is we look at these two here, and this is going to be a 1, 1, 0, 0, 0, 1, 0, 0. You would then look at that right there. You do it step by step. And you come up with that right there. So this is the process you would go through and generate a truth table from a circuit. You will be expected to know how to do that on the final exam. Everyone wants to hear what's going to be on the final exam. It's 60% of your grade, right? So right there. So I'm just pointing out that this lecture covers probably at least one of the questions with multiple parts on a final exam. Will come out of just this lecture right there. So as you make notes of lectures to go back and review, this might be one. Not there. So, that there. Logic can be from a circuit diagram. That there. Again, we're going through here, and this is really the same thing. Now, what I want to do is kind of go through here, and I want to probably let me finish this discussion, and then I'm going to take a little break, and I want to bring up some software that I want to use that we'll be using from time to time there. So it's important to draw from its Boolean expression. Again, this is the process where we come up with right here. So notice here that we're showing these terms right here. So those would then that's the final output. And this is the circuit here. So as we go back and we look at right here. Okay. All right. I was hoping that they gave me the circuit right here. All right. Well, here they gave, in this particular case, you're given the equation. You're expected to come back to the circuit right there. So, and they did this kind of backwards because they should have gave you this first right there. So if you're given this right here, we see that our top level is an OR gate with 3 inputs right there. So there's our 3-input OR gate. Our first one has A and C going to it, so that's this one right here. The next one has got B, C naught, so that's this one here. Here's B, and then we show here's our inverter to get B naught, or C naught, excuse me. Then the last one, we put the inverter to get A naught here, right there. Later on, we're going to be looking at other types of logic where we use what program logic arrays, where we have a whole bunch of these at one point. But this is actually what they call a sum of products standard way of writing the equation, right there. You'll hear this used SOP. That's not standard operating procedure, but sum of products. Right there. And that's one way of writing Boolean expressions. Every Boolean expression could be written by a sum of products. Right there. And we'll get into how we would do that. Once we have the sum of products, then we can draw our circuit from that. So I can go from a truth table to that there, easily from a truth table to a drawing. Is it the most efficient drawing? We don't know yet. We'll be using tools to simplify our circuits. So, but what we started here with, if you have a standard sum of products notation, you'll look at the number of terms. These are terms. We've got 3 terms. That tells me that my last stage is going to be a 3-input OR gate. If there's 4 terms, it'll be a 4-input OR gate. 5 terms, a 5-input OR gate. So we would have an OR gate for our last term. Everything beyond the OR gate will be AND gates. These are our product terms right there. And then we would look at each of these terms to determine what the input is to that AND gate. So an example of that, and I keep going away from the slides, and unfortunately, as I said, I'll probably do this and then I'll discover that, let's say I do an expression here, A not B, B C, or A B not, or C is equal to X right there. So this is a 3-input OR gate. So I look at this here. So this is a standard sum of products right there. It has 3 terms right there. 3 terms. So I know that my last stage is going to be an OR gate right there. So I have 3 terms going into it. The first one is an AND gate. It's got three inputs. And it's got A going through an inverter right there. It's got B and C. That goes to here. My second one is also a AND gate. It's got A, so I just pull A down. And it's got B not, right? So I put my inverter in here right there. My last one I don't need an AND gate for because it's only got 1 term. So I just have C coming into that right there. And that's my circuit right there. So going from the equation to the circuit, if it's in standard form, it's very easy. Very easy. Now this may not be the simplest circuit right there. So this is, he's probably got more examples here right there. Again, circuit diagram to implement here. Now we've got what's called a product of sums notation, where we reverse that there. This is now a product of sums right there. So what we've got here is we've got multiple terms that are multiplied together. Each one of these has got a plus sign or a single variable in that there. So this is standard product of sums. Now, later on, we're going to look at how we can go back and forth between these. But again, in that case, the last stage is always going to be an AND gate. And then the previous stages are going to be OR gates. Right there. And we look at this right here comes from here, this right here, right there comes from that there. So it's very, very straightforward and easy to do a sum of products or a product of sums. Now you'll see a mixture of those early on in the semester to kind of go through that there. But typically when we're dealing with more advanced circuits, we will almost always stick with a sum of products or a product of sums right there. And there's a reason why we do that. And we'll see that toward the end of this chapter. We'll see the reason why we do that. All right, we also have 2 other types of gates, and those are the NOR and the NAND gates, and they're basically inversions. All we've done is we've taken and we put that little bubble I talked about right there. So the OR gate is only high here. Now it's low. We just inverted the output there. And we've just shown here, this is just a waveform. We'll get into some software where we generate waveforms here in a minute. But this is A and B not, or NOR. A or B, no, not, or NOR. A nor B. We also have the AND gate that's inverted. So those are our 5 basic gates right there that we will use. And we will use those probably for the first 4 weeks or so, and then we'll get into some more additional circuits right there, 3 or 4 weeks. Right there. So again, we get into, here's a messy looking circuit that's not of that form right there. But you can see what we've done here is we could rewrite this actually. And I'm just going to rewrite this as A or B or C plus D not right there, and then a not there. The reason I did that is so that you can see that this is a 3-input NAND gate at the end, and you see that, and what makes it a NAND gate is that we have this line across the top. I'm going to stop this discussion here at this point here, and I want to spend a few minutes talking about right there, and I will post this file up later on out there. I don't guarantee I'll get it up today. It may be tomorrow when I get it up. If I don't get it up, someone send me an email, remind me to post chapter 3 slides out there. But I'm going to probably go upstairs and decode, get the video posted at the same time I post the video. I'll post these slides out there. And these slides actually have for like the next week and a half's worth of lectures on. Okay, there's a software package that we're going to be using here, and I don't know where if it's installed on these machines. I will at there. It better be on this computer. I know I put it on this computer. There it is. Quartz. I know that they've got the software on campus. Just find out which lab it's installed in. Oh, it's right here. This is the software that we'll be using, and I don't really expect you to, and to be honest with you, it's very difficult to use the software with this projector, but I'm going to go ahead and try doing it there. But this software here allows us to draw a digital circuit and then see what the outputs are for various things. And this is more of a demo than it is trying to teach you how to use it. There's some tutorials in, I believe, the Floyd book, or both the Floyd and the Tochi book, on how to use this software. But we're going to create a new file, and we're going to draw a schematic right there. And I'm just going to implement some things right here, symbol tool. And I'm just going to draw a circuit. And I don't have anything to use to draw that here, so I'm just going to make this circuit up right there. You know, actually what I can do is, let me just basically use this circuit right here. So I want to do the circuit A naught B C plus A B naught plus C. That's the circuit I want to draw right there. So I'm going to, the reason I put it there is because I can go back and forth between that, really easy to see. So I'm going to go through, and I'm going to input a, let's see, that was an OR 3 right there. So that's my output for that right there. Right there. So then we're going to input another one. We need a AND 2. Let's see what we got here. An AND 3, right? An AND 3 and an AND 2. So let's go through here. Let's do a AND 2 right there. And then we need an AND 3 right there. And then we need, it looks like one inverter, right? Two inverters. A NOT. Right there. So we're going to hook this up right here. Right there. So, and this should look very similar to some other software you might use, but right there. Input, we need 3 inputs, right? So I'm going to click repeat mode there. And I'm going to just put them here for now, and then and the reason I'm going to put them there is because I need to put them that there. And what we go ahead and wire this up here. The first one is going to be, let's go ahead and take the, right there. Right there. And then we're going to So on this one here, so this is supposed to be B there, right? And B also goes into here, right? So let's put B. Actually, worked for a guy one time. He said he was glad he didn't hire me as a draftsman because I'm not a very good draftsman. Right there. That looks like it's connected. You gotta be careful when you move these things because sometimes they'll. Right there. And this goes up to, this goes to B there, right? And this one went to where? A. And then we need one more, we need an output. And this was what, A. B, C, and this over here, X, right there. So this is our basic circuit right there. And what I want to show is that once we draw this circuit, we can then simulate this thing here and see what the output should look like. Now this won't give us a truth table, what this gives us is a timing pattern right there. So first thing we need to do is go ahead and save. And I'm just going to call this digital 1. And we're going to call it digital 1. 1. And we're going to create a new project for it. And I'm just going to, all right, I'm sorry folks, I have to do this for a minute. And the reason I have to do this is the screen resolution is just horrible. With this software, this software was designed back after and I'm just going to, you know what I'm going to do is I'm just going to, since we're just going to simulate it, I'm just going to skip through these here. Right there. Okay. I'm not going to apologize. I didn't buy the equipment that they have here, and I am not responsible for updating it, but obviously that's a problem. So once we have that there, we go ahead and we can compile this to make sure, and there's no errors in it right there. Right there. It takes a while to compile. Right there. So now, as it turns out, this is actually compiling it for a chip. But what we want to do is we want to just see what the outputs, and it gives me some warnings here, which we're not going to worry about those warnings. well, what I want to see is what the output's going to look like with respect to the input. So let's go ahead and create a new file. In this particular case, we're going to list all. There's all of our pins right there. I'm going to make some, I'll get into the reason why we did do this here. Grid size, we're going to make this 50 nanoseconds. And I'll point out the reason I have to do that later on. We'll get more detail. Then we're going to group these right here. Group and inputs right there. So that just shows A, B, and C right there. And value count. Right there. Value. Right there, and let's, as you can see, there's our inputs looking like this. Now A is our most significant bit, C is our least significant bit. So at this point, we've got, those are our inputs. So now at this point here, I can go through here, and first thing I need to do is save the file. Right here. And you can see this is what the output should look like here. So if from the truth table, this would be 0, this would be 0, 1, 0, 1, 1, 1, 1, 1, all the way down to that there. So this actually gives me what the truth table is for that circuit right there. But it gives it to me on the way I would see it on a scope. Now what you do see here is that you'll see a delay from here to here. Everyone see this delay I'm talking about? Right here, let me change this to an arrow. You see, here's where all the inputs change. But the output doesn't change until a few, see this right here is set for, that's right at 50 nanoseconds. And then here at about 58, 59 nanoseconds later is when the output changes. So there's a 9 nanosecond delay going through this jet. And that's why if I left it at 10, it wouldn't make any sense. All I would see is the delays. The output wouldn't make any sense. So you have to change it to where you're seeing, you still see the delays. See, right here the output goes from high to low, but it takes about 9 to 10 nanoseconds from the time that it actually goes low here. Right here. You see right here is where, right here at 100 nanoseconds, the inputs change, and the outputs don't change until about 109 nanoseconds later. So there's almost a 10 nanosecond delay going through the jet. Now, if I had the board here, I could actually download this to the board and flip the switches and see that I get the same result. And that's what we'll be doing as far as seeing how these work, because we'll be running these on development boards. If this was, of course, a technology program, you would buy a bunch of TTL chips and you wire them up on a board and put jumper cables in between. I'll be honest, nobody does that anymore anyway. Not there. A colleague of mine back in the U.S., he liked to make people do a final project in the basic digital course, and he had this long project where they would sit down there with Carnot maps and they'd have all these circuits and all these counters that they would come up with. And it'd be like 12 ICs, it'd be wired up, it'd be a big mess on a great big board, and then they would run the project and see if it works. And then when I took the second digital course, my first job was, let's take your final project here and let's put it on one chip. Right there. So we're going to just jump straight to the one chip solution. Right there. we'll talk about multiple chips, but most people are using programmable logic for this. But we can still cover everything, but use programmable logic for seeing how things work. So with that said, my rule is I talk about an hour, and that's about all I'm good for, and I'm starting to feel myself go here. So, any questions on where we're at? A lot of material today. A lot of material today. So, with that said, let me stop this right at 1 hour. Right there. So.